So, you have launched a spacecraft to Mars, the orbital calculations were on point, and you are actually traveling to the red planet. Now what? We need to get from here to here. And we want the rover to be hopefully in one functioning piece. How do we do that? With lots of math, physics, and smart controlling methods and algorithms. This is a short video about EDL, Entry, Descent and Landing, or sometimes also called the 7 minutes of terror. First of all, there are some limitations we must consider. Since we are near Mars, the communication is delayed by about 15 minutes in each direction. This means that real-time control from Earth is impossible. While some correction maneuvers can be made before reaching Mars and setting up a good trajectory to the atmosphere, EDL needs to be automatic. Another limitation is the accuracy. The team that designed the payload wants to land as close as possible to a certain target. After all, you do not want to end up on a mountain 500 km away from the crater you wanted to explore. Shown here are the accuracy ellipses of different Mars missions, projected on Earth and centered around Würzburg. The 1996 Pathfinder mission is shown in blue, while the InSight, Curiosity and Perseverance missions are shown in purple, red and orange respectively. The Mars 2020 Perseverance rover had a landing ellipse of only 7.7 times 6.6 kilometers, making it possible to select new targets where only a small area has a suitable landing space. This video focuses on the recent Mars Science Laboratory or Curiosity and Mars 2020 or Perseverance missions, which feature modern, accurate EDL systems. The vehicle consists out of the cruise stage, entry aeroshell, descent stage, the rover, and the heat shield. Before even coming close to the entry, the spacecraft is in the cruise phase of the mission. For this reason, the cruise stage exists, which main function is to interface to the launch vehicle and provide the structural support for the rest of the spacecraft during launch, and then to provide power, telecommunications, navigation, and propulsion for the 9-month journey from Earth to Mars. During this time, the spacecraft is spin stabilized, and multiple trajectory correction maneuvers can be made to optimize the Mars entry target. Right before entry can begin, a sequence of events needs to happen. First, the EDL behavior is initialized, entry thrusters are preheated, and the current attitude is measured using a star sensor. A last TCM can be made at this time too. Then, 10 minutes before our entry, the cruise stage is decoupled, after which the entry vehicle despins, since it was spin stabilized till this point, and orientates towards the entry attitude. Because entry should be a guided and controlled one, two balance masses are separated. This results in an offset center of gravity, and therefore in an angle of attack of around 20 degrees, which results in a lift-to-drag ratio of 0.24. Atmospheric interface starts at a distance of 3,522.2 kilometers from the center of Mars. While Mars has a small and thin atmosphere with only 1% of Earth's atmosphere's density, entry still needs protection, which is done by a heat shield made of phenolic impregnated carbonablator, or also known as PICA. During entry, the vehicle is controlled by 8 RCS entry thrusters. To improve the landing accuracy, a guided entry is flown. The guidance algorithm consists out of 4 separate phases. After entry interface, the vehicle is in the pre-bank phase, in which the bank attitude is being held constant. When the deceleration exceeds 0.5 Gs, the range control phase begins. Since the vehicle has a lift-to-drag ratio, which is not zero, it can fly and control its lift vector. The goal of this phase is to minimize the downrange error at parachute deployment. This can be done by flying role reversals, where the spacecraft banks from one side to the other, to burn more energy and basically fly S-turns. Peak heating also occurs in this phase of entry. After the velocity is below 900 meters per second, the heading alignment phase begins, where the bank is controlled so that the cross-range error gets minimized. Shortly before parachute deployment, the last phase of entry starts. The angle of attack of 20 degrees is no longer necessary, so more masses are ejected to return to an AOA of 0 degrees. Also, the roll attitude is changed so that the radar has better scanning angles later on. All in all, the entry phase started with a velocity of roughly 6,000 meters per second and ended with a speed of 450 meters per second. With an entry mass of 3,257 kilograms, which is roughly the weight of a Cybertruck with 2 occupants, this equates to a kinetic energy equivalent of 12 tons of TNT, which is being dissipated during entry. Here you can see a simulation of 3 different entry trajectories. Each one has a different amplitude of its role reversals. The green trajectory has full reversals from -90 to 90 degrees, while blue has none and orange has reversals from -45 to 45 degrees in bank attitude. On this graph you can see the height plotted over downrange, clearly showing a different lift characteristic and the following landing distance change. This simulation only takes gravity and drag into account, with a parachute opening at 10,000 meters in altitude. For the individual drag calculations, a constant ballistic coefficient is assumed. Also, the atmosphere rotates at the same speed as the planet, hence the sideward deflection at the end of the trajectory. Descent can be generally divided into unpowered or parachute descent and powered descent. While on Earth it is possible to descend and land with only parachutes, the same thing cannot be said about Mars with its thin atmosphere. Still, parachutes provide a simple way of slowing the vehicle down from supersonic to subsonic speeds. While MSL used a velocity trigger for the opening of the parachute, Mars 2020 used a range trigger, which reduces downrange error. For MSL, the speed was roughly Mach 2, which means that the parachute decelerates the spacecraft from 450 meters per second to 100 meters per second in roughly 50 to 90 seconds. An often used type of parachute for this application is the disc gap band parachute. In our case, the Mars 2020 chute had a diameter of 21.5 meters. For more information on parachutes, please check out this video on the channel, which covers the topic of parachute landings in spaceflight. Upon opening of the chute, the capsule beneath may start to rotate violently around its center of gravity. This motion, also known as wrist mode, needs to be dampened with RCS in order to separate the heat shield safely and for the radar to acquire the ground. Speaking of the heat shield, since we are now subsonic, heating is not really a problem anymore. We want to separate it and give way for the powered descent vehicle to separate later on. The separation needs to happen without recontact. Therefore, the ballistic coefficient of the heat shield needs to be higher than the rest of the vehicle. Due to transonic drag characteristics, this can only be guaranteed below Mach 0.8. Till this point, the vehicle was using IMUs for any navigation measurements. But since the powered descent and landing is going to happen shortly after, we need a more accurate measurement. The Terminal Descent Sensor, or TDS for short, uses 6 different radar beams to measure ground relative altitude and velocity. Because the heat shield was just separated, it also must be certain that no more than one beam is being covered by the heat shield. So an additional time of 5 seconds after heat shield separation is added, where the navigation system expects bad radar data. While the 6 beams look in different directions, the real landing site might not be covered by one of them, resulting in a possible error. This also limits the landing site to a certain flatness, since the radar is susceptible to large terrain height variations on a small area. Mars 2020 also uses terrain relative navigation to select a safe landing target in the landing ellipse, which makes it possible to land in areas with more dangerous terrain. A video on TRN will be or is already available on this channel, so check it out for more information. The goal of the powered descent is to fly the powered descent stage to the starting point of the sky crane landing maneuver at 18.6 meters in altitude and 0.75 meters per second vertical and no horizontal velocity. While still connected to the back shell with the parachute, the 8 engines are throttled down to an idle state of 1%, and pyro valves are fired open to allow fuel flow. Also, with the data from the TDS, the altitude at which powered descent needs to start is calculated. Once this altitude is reached, separation nuts are fired, which disconnects the landing vehicle from the aeroshell. After a second of freefall, the engines throttle up, and a 2.2 second period begins where any altitude movements are stopped and a predefined altitude is being assumed. During powered approach, the landing vehicle follows a trajectory calculated at backshell separation, where the horizontal movement is slowly stopped and the vertical speed is reduced to 20 meters per second. This phase ends roughly 100 meters above the surface and at a perpendicular distance of 300 meters from the entry trajectory, helping to avoid recontact with the aeroshell and parachute. The TDS altitude can be off by 50 meters at backshell separation. To allow this area to fly out, a phase of constant velocity, called constant velocity accordion, is added. For an area of minus 50 meters, the CVA duration is 0 seconds, while for an area of plus 50 meters, enough additional fuel is needed for the 100 meters or 5 seconds of additional height. After the CVA, the vehicle is at 50 meters in altitude and the constant deceleration phase begins, where the vehicle slows down to the target vertical speed of 0.75 meters per second. The last phase of descent is the throttle down phase. Since the velocity needs to be constant again, the engines need to throttle down. But instead of throttling down all 8 thrusters to inefficient levels, 4 of them are instead reduced to idle, utilizing only the remaining 4 engines. This might add additional disturbances, so a 2.5 second settling time is added. The vehicle came into the atmosphere with a speed of 6,000 meters per second and is now hovering just above the Martian surface. Now only the landing needs to commence. The MSL and Mars 2020 missions use the sky crane to land the rover. In this maneuver, the rover is being descended from the hovering descent stage. This method has advantages over legacy methods such as airbags and legged landers. First, the engines are far above the ground, leading to less dust excavation and trenching, while still having full control of the landing in contrast to bouncing in an airbag. Also, a complex egress phase is no longer necessary, since the rover directly lands on its wheels and suspension. Right after the throttle down, at an altitude of 18.6 meters, the rover and the descent stage are separated. While still descending with 0.75 meters per second, the rover is being lowered on 3 cables to 7.5 meters below the stage, which is lowered using an electromagnetic brake. To prevent any disturbances to the descent stage, the 3 cables run through a single hole located close to the center of gravity of the descent stage. During the lowering, the rover also extends its mobility systems to absorb the impact of landing. 7 seconds after separation, the rover is dangling the full 7.5 meters below the descent stage. The cables are at the end of travel and the motion of the cable stops, which is called snatch. Another 2-second margin is added for the descent stage to stop any disturbances caused by this event. Then the touchdown logic is started. Instead of detecting the touchdown with an additional sensor, which could fail, the commanded thrust is being monitored. Since the descent stage tries to descend with 0.75 meters per second even after the rover is already touching the ground, the needed power for the descent is drastically lower than when the rover was airborne. This change can be detected and is used to declare touchdown. Once this happens, the descent stage stops its vertical motion. Then all 3 wires are cut and retracted using springs. Also, the umbilical is cut and the control is given to the flyaway controller. The altitude is held for a short period of time for the cables to retract, then the 8 engines throttle up to 100%, and after an additional time the stage pitches to 45 degrees and burns its remaining fuel. This means that the descent stage crashes at least 150 meters from the rover. When all hardware reaches a velocity of 0 relative to the Martian surface, EDL is completed, and if the payload is undamaged or at least not destroyed, it was a successful EDL.